before you found the solution of home tasks, please calculate the E2, which is the trace of L square.
So on the diagonal, it's A1 squared. The trace. AJ squared plus BJ squared.
But here's the sum from 1 to n, and here the sum from 1 and minus 1. You remember that it is root 2 of the Hamiltonian. So our Hamiltonian is part of this family of integrals constructed from the Lux Lux matrix. If I remember well, there were questions about the integrability of the Kepler problem, and
we have to calculate the Poisson structure of H and F.
Kepler problem and the Euler top also. Is it integrable? So let us discuss this. Liouville integrability of the Kepler problem and the Euler top. Let us remind the definition of the systems, and let us try to understand what is needed for such statements. Maybe let us start by the Kepler problem. Do you remember the definition of the system, the definition of some integrals? We have found integrals which are just the angular momentum vector. So it has 3 components. All these elements are integrals of motion, but they are not commutative. It's not an involutive family of integrals. So my statement is that despite this fact, the Kepler problem is integrable, and we have to construct an involutive family of integrals. What do you think about it? Do you remember the definition? Could you write all what is known? The Hamiltonian, the angular momentum, the brackets. So maybe we will find the solution altogether. If I remember well, it's minus alpha over, but minus. Do you agree? Yes, it is minus alpha. Yeah. Okay, and we have found 3 integrals of this motion. But I'm sorry, what is the Poisson structure?
So alpha is some parameter.
Yeah.
And
Posit-
R is the distance between the objects.
R is the, yes, is the length of the radius vector. What is the Poisson manifold here? So it's some space with the Poisson bivector. Just R6. So three components of coordinates and 3 components of the momenta is R6.
So then the integrals were
What's the Poisson structure?
So Poisson structures is just Poisson breaks.
And I'm sorry, traditionally we denote by Q the coordinates and the momenta by P. So here P, yeah. Perfect. So we have coordinates P and Q. P for momenta and Q for coordinates. And R is the square of Q okay. So what are the Poisson brackets between variables P and Q?
Is it something specific or as usual?
No, it's a standard Poisson bracket.
Okay.
Just a standard Poisson bracket between Pi and Qj. It's a delta function. It's a delta function. Yeah. Okay. Angular momentum. What is it?
I will just
It's angular momentum.
Okay. I propose to use here Q. It's R is the length of this vector, and Q is the vector. Yes, that's right.
and I don't remember we found all integrals or just on the component of momentum is integral of motion.
Yes, we have demonstrated that it's L.
Yes.
It is 0.
Yes.
It's a vector. You see, this is a vector, and this is a scalar function, so it's 0 as a vector. So all components, so it's the same as Li is equal to 0.
And we need to find two others integrals, right? The question.
You see the situation. On our 6-dimensional space, we have 4 integrals because the Hamiltonian is also an integral. But the components of the angular momentum are not in involution. Do you remember the Poisson brackets between components of the angular momentum?
Minus or plus
It should be plus, I think. Very good. So now we need to construct an involutive family. How much integrals do you think we should find?
Well, this the third is Hamiltonian himself. And the fourth is this R square.
Yes.
And
But we need 3 integrals. The Liouville integrable system on the 6-dimensional symplectic manifold is given by the choice of 3 involutive integrals. Now you found 2. We need the third one.
no, can't I use this integral? No.
For which I?
Like, let's choose I.
3?
Yes.
Uh-huh. As you like.
So we have three integrals and
Why are they in involution?
evolution means
That all Poisson bracket between integrals. So you like to say that L square and L3 is an involutive family?
yes.
Why?
Well,
So you know this? So this is clear that H with L square is 0.
yes.
And this else.
Yes.
Why this Poisson bracket is 0?
Well,
Because we have
if you,
evolution, and we can, if I put, we can actually calculate this, I think.
if you take the Poisson brackets between them, we should be 0 as well. No?
Why?
Well, if you calculate it straightforward,
Yeah.
it will be pretty long, but clear. But
Yes, you are right. You are right. And we have done such an exercise. So we have already calculated that this element lies in the center of the Lie algebra SO3.
okay.
You see, these generators, they produce the Lie algebra SO3, and this element is a central element here. Do you know the geometric description, the geometric motivation, why this is the central element?
Well, it's a describe three-dimensional sphere rotation.
Yes.
And L2 in the center means, yeah,
It's a distance. It's a length of a vector.
yeah, it's always the same.
It's always the same if you do the rotation, the orthogonal rotations. So it's a central element because it's a constant with respect to rotations.
So it's just like a radius.
Yes, yes, of course. Okay, and what is the final statement? So we try to motivate the Liouville integrability of the Kepler problem.
I mean,
Is the Kepler problem integrable? Liouville integrable.
say it again. What is Liouville integral?
If you have the set of independent integrals in involution.
Oh, then yes, because we have a set H square of 3 which Poisson brackets is always independent. And
So they are in involution.
yes.
And they are integrals because they commute with the Hamiltonian. Why are they independent?
They are independent because the Poisson brackets between them are 0.
No, no. Functionally independent.
Oh.
Maybe they are dependent. So maybe in fact, they correspond to some smaller number of functions. If for example, you write L3 and L3 square, this is also the set of 3 integrals in involution, but they are dependent. This function could be expressed only in terms of this function.
Oh.
But if you calculate the differential as an element of the cotangent space, they will be dependent. Why these functions are independent? Do you remember the definition?
Definition of independence.
Yeah. It's just the rank of the Jacobian matrix. We have to calculate, so here are some functions, h. We have to calculate dhi or dxj. They're These are the coordinates on our Poisson manifold. And we ask for the rank of this matrix to be n, which is half the dimension half m. So you see, we have coordinates p and q. P and q. I think it's better to write it down. Let's try to write, because it's also an important exercise.
So what should I write?
The derivatives of these functions in terms of coordinates on our space. So we have x1, x2, x3, x4, x5, x6, who are p1, p2, p3, q1, q2, q3. As you like. L3 is the most simpler. Mm-hmm. I'm not sure about this. What do you mean here? Yeah. Uh-huh. Mm-hmm.
So it should be like
If J is from the first triple, this is 0.
yes. Yeah. And this is
This is just delta.
so it's just plus. Should I write Carnecker symbol?
No, this is not true. So this derivative is a constant vector, yes, with 1 on the Giff place.
Yes.
Okay, so it's something like this: 1 on the Giff place, and with Q.
Yes.
The same. Yes, but if this index is on all this set, so it would be on the 3 minus g place. I'm sorry, g minus 3. G minus 3 place. You understand? So because the Q2 is x5, but maybe it's not the best way to write it down in general, for the general I. I propose to you just to write the third component of this angular momentum, and this is P1 Q2 minus P2 Q1. It would be more What is the dl3 dxi? It's a vector. Just one on the first place. No. I think it's Q2 when you differentiate with respect to the first coordinate. It is Q2. If you differentiate it with respect to the second coordinate, which is P2, it is minus Q1, 0. Could you write the rest? Because it doesn't depend on P3, but it depends on Q1. The next component is the differentiation with respect to Q1. No, it's minus P2.
No,
It depends.
Like 0, like this still.
It is on the third place. It's the first, second, third place, and the fourth place. It's the differentiation with respect to Q1, and it is minus P2. The differentiation with respect to Q, yeah, very good. And here 0, yes. So it's a line in this Jacobian matrix. So it's a little bit more complicated. I propose to write it in coordinates. Firstly, what is the L square? Yes, but in P and Q. No, this is not correct. I think the only way is to write all components in coordinates and try to understand how to gather all terms. Minus P2 Q1 square. Why there is square root? I think it's just the yes, it's polynomial. Mhm. Ага. Окей, окей. Да, только подожди. No, we will need it. Ага. Okay, with respect to P1, so it's PQ, PQ,
Yes.
PQ, PQ, PQ. So with respect to P1, there are two derivatives here and here. Aha. It will be square, the component and multiplied by Q2.
L1
I think it's better to write in coordinates. Maybe they will cancel each other. Just in coordinates, yeah. Just the complete form. Let's try. Maybe it will work. Just a complete form like this. I suppose that it will cancel with something else. P1 Q2. Q2 minus P2 Q1 multiplied by Q2. When we differentiate over P1, it is multiplied by Q2. We calculate by x1, which is P1.
Yeah, but it's square.
Yes, this square. Okay?
Yes.
And there is another term when we differentiate over P1, which is minus P3 Q1 minus P1 Q3 multiplied by Q3. Do you agree?
Yes.
Okay, let us see if there are some interesting.
I mean, we just can write full vector.
It's the second,
Yes.
but it's not the sum. They are
No,
different
it's-
components
yeah,
of
it's
this
first
vector.
and second.
So it is quite difficult to understand if they are dependent or not. But maybe it's simple to see that the third component will be non-trivial. Third and the sixth components are non-trivial. But you see, even it's better to consider two such functions as the functions on this just on angular momentum. They're independent because angular momentum are just different coordinates. So it's easy to see that these functions, as functions on this space, are independent. But how to demonstrate it that H is independent with them? So I prefer to leave it to the next Monday, just to demonstrate the independence of this function. Home task.
Well, sorry, I just mean that our L is P vector product Q, right? And L square is this thing, inner product itself. So it's equal to P square Q square minus the square of P inner product Q. I mean, you get?
No, I don't understand. Could you repeat?
Yes, L square is L inner product itself, right?
L square, yes.
L inner product itself.
Yes, of course.
It is P vector product Q inner product P vector product Q.
Like this?
Yes.
Yes.
And it is P square Q square minus the inner product of
P square.
Q square. Mute class. P square multiply Q square.
Why?
Because it is the property of inner products and vector products.
P square, but multiplied by.
Minus.
Yes.
And then minus the inner product of PQ.
Of PQ. Aha.
And
Square.
Yes,
Aha.
that's it.
Yes, that's right. Yes.
Yes, and it's much more easy to calculate the derivative of this thing.
Yes, I agree. Yes, I agree. Okay, maybe we will try to calculate the derivatives. So dl square over dpi.
It's just pi times q squared.
Pi, 2pi times q square.
Minus 2, the inner product.
Yes, it means that it's qi, pq.
Yeah.
Very good, very good. And could you calculate the derivation with respect to p? It's quite the same, but with q. Mm-hmm. Yes. Maybe it's okay. Now let's calculate the differential of h. R power 3 over 2. R power 3, yeah. QJ. Just QJ. PJ. Just PJ. Let's combine the complete Jacobi matrix with all differentials. The matrix 3 by 6, and maybe it's better to start with this component of the angular momentum and the Hamiltonian, but please keep enough place for the components of these derivatives.
Maybe it's easy with 6 by 3.
As you like. As you like, yeah.
Should I build by all volumes or just by the symbols?
Yes, you have to place all correct. Q1, yeah. You start by Q, because here we started by P. P1, yeah. P2, P3, very good. So Q1 over R3, yeah. Perfect. Next one, the differential of L3. Q2 minus Q1, 0. Q2, minus P2, P1, 0. Q2. And then this one. So we start by differentiation over Pi, P1. So it's 2P1 Q square minus 2Q1 2P1 Q square minus 2Q1, the scalar product PQ. Next, P2, 2P2 Q square minus 2Q2, the scalar product PQ. The next, 2P3 Q square. Okay, next returns comes from your calculation. Okay, I suppose that there is enough information to understand the independence. What do you have some ideas? you see, we have to find a minor 3 by 3 which is non-zero to demonstrate that the rank is 3. Okay? You see, there is some element here, p1, p2, p3 multiplied by the same component. So if we multiply this by q square and subtract, we can cancel these terms. So I prefer to consider this minor and to do some linear transformation with this matrix. And the first one is what I said. If we subtract the first line multiplied by 2q square from the third line, q2 minus q1, q1 0, minus 2q1 pq. So this will cancel. Minus 2q1 pq. Minus 2q2 pq. And minus 2q3 pq. What else?
Well, PQ is
It is evidently that this constant could be put in front of the matrix.
and we left with Q2, Q1 here. And
So in fact we have such a matrix P3, Q2 minus Q1, and Q1, Q2, Q3 multiplied by something. But what do you think about this matrix?
Its rank is 3.
Sorry?
Its rank is 3.
In a generic point, yeah. Yes. But why?
Because these are independent variables.
This and this, not. So these two vectors are independent, yes. In a generic point, it's two generic vectors. But this vector is, in fact, could be dependent. I think now we need to calculate the determinant. But it is quite easy now.
yeah, but
There are two terms.
should I calculate? Or
Yes, there are. It is quite simple. We need to use the rule of decomposition of the determinant with respect to the third column. So this term multiplied by this determinant plus this multiplied by this.
so again, what happens? Just
The decomposition of the determinant with respect to the column.
yes.
Разложение по столбцу.
Then I would
This multiplied by this plus this multiplied by this determinant. Because it's zero here.
Yes. It's the same, just
Uh-huh. With minus. Uh-huh. This is minus. Uh-huh. It's better to, uh-huh. Uh-huh. Okay. So we have to say that it is a non-trivial polynomial. Okay? So in a generic point, it is not it's not zero. No, it's Q. Mm-hmm. Mm-hmm. Yeah. So it's not a trivial polynomial. It means that in a generic point it's not a zero. Okay? So that's why our functions are functionally independent and provide an integrable structure for the Kepler model. Okay, thank you very much. Please take your seat. What should we say about the Euler top? How it is also integrable, but in a little bit more. Yeah. Do you remember its definition in terms of Poisson structure, angle, momentum? So there is also L, which is PQ. There is L square, which is an integral, and there is a Hamiltonian, which is L1 E1 and they commute.
I think the simplest way or the way I do it, just find the derivative of
What is the dimension of the Poisson variety? No.
6 or 3.
No. It's not 6. Even this is not, it is formulated just in terms of the angular momentum. Do you remember? It is written like J is what? J IJ, something like this. I'm sorry, L. What's L? L dot is L I L. This is the equation of motion for the Euler top. So it is described in terms of just of angular momentum vector. The phase space is three-dimensional. It's the same. It is described by SO3 Lie algebra and of its symmetric algebra. So, but the phase space is three-dimensional. And what could you say about the Poisson bivector? Is it degenerate or not degenerate? Yes. Does it have a kernel, non-trivial kernel?
If it's non-degenerate, then it should have.
So it's the story of the center, Casimir functions, and symplectic leaves. We have discussed this structure for the reason of the good description of integrability property. So this was not for amusement. So in this case, the Poisson bivector is degenerate. And you know that there is a central function, the Casimir function. L square is a Casimir function. And it means that for a generic value of L square, the subvariety L square equals C is a two-dimensional symplectic variety. You see? So on this subvariety of the three-dimensional space, you can define the symplectic structure. So it means that on this subvariety, the Poisson bivector is non-degenerate. And in this case, we have to demonstrate the Liouville integrability because it works only on symplectic varieties. And in this case, it's a two-dimensional variety, and we have to found only one integral. And this is our Hamiltonian. So you see the Liouville integrability of the Euler top is done by two steps. The first step, you have to choose the symplectic leaf by fixing the value of central elements. You obtain a symplectic manifold, and on this symplectic manifold, you have to find the sufficiently large family of involutive integrals. In this case, you have to find just one integral, which is a Hamiltonian, which is functionally independent on the central element. For generic values of inertia indices, these functions are independent. They are different quadratic functions. You see? So you have to sit on the level set of the Casimir element and on this two-dimensional symplectic manifold to consider Hamiltonian model with one Hamiltonian. It is integrable. Okay? So, and this is given by fixing a plane, you know. Okay. Okay. We go to the Toda system, and let us discuss the theorem of Lax representation. Let us do this home task today, now. I will write all necessary things on the blackboard, but you have to demonstrate the theorem. So I recall you the Flaschka coordinates. The Flaschka coordinates the equation of motion in Flaschka coordinates. the Hamiltonian Flaschke coordinates and the Lux matrix. And the matrix L plus minus, which is B1 so our statement is that the equations of motion is equivalent to such an equation ML. Let us do it now.
It seems like we need to write the explicit form of matrix of L and M, isn't it? And then we can differentiate.
Yes. Maybe it's a little bit more easier to introduce this decomposition. Lambda, which is the diagonal part, plus this part, I don't know how to say, B, and plus B transposed, which is this part. So here D is just a diagonal matrix composed of A coordinate, and B is Bn minus 1 upper triangular matrix of the first diagonal over the principal diagonal, and M, in this case M is B minus B transposed. Maybe this will be more convenient.
But you need to represent this L with those coordinates. How it's called?
Flaschke coordinates.
Flaschke coordinates,
Yeah.
isn't it?
Yes. These letters are Flaschke coordinates.
I solved the Flaschke coordinates.
Yes. Yes, of course. But
Then you need to find the commutators.
When you look at the first beam and you compute it with this,
mhm.
we are only left with D plus B transposed.
Mhm.
And here we are left with this.
No, yeah, very good.
Then further, there is
Plus.
and I think these cancel.
No.
No? Okay.
So it doubles. You see?
They did.
Yeah. The same.
They're the same.
Uh-huh.
Okay. So this is this.
Uh-huh.
And I think we can also notice that D is the same as D transposed.
If you like.
Somehow, I don't know, maybe there's no, we can't simplify it further.
But it is already quite symmetric. So you see, this is the upper triangular part.
So this
You see?
commutator is upper triangular?
Yes, because it is upper triangular, this is diagonal.
Okay.
The diagonal with upper triangular produce upper triangular. This is lower triangular. And the diagonal terms comes from this one. So you see, quite rapidly, you get you get the derivatives of the diagonal, of upper triangle, of lower triangle terms.
So I mean that we look at this, and we say that and we are supposed to say the following.
I'm not sure that here you get only the diagonal.
Not only, okay, yeah. Okay.
Okay?
Yeah, yeah.
It is sure that here you get only upper triangular.
Okay. So we can identify this with this commutator.
Yeah, yeah.
Okay. So this holds,
Yes.
and I think
This else, yeah. But you see they are equivalent,
Yeah.
because as you remarked, D is symmetric, and this and the transposition change these signs. Okay. So this is a consequence of this. These two qualities are equivalent.
Okay. And so this is true.
This is true, and maybe it will produce the evolution equation for B's.
Yeah.
Because you remember, B is composed of B's.
Yeah, we just have to verify that.
Yeah.
Yeah, but if we say that this is correct, then from that it follows that the derivative of D is this term. I think maybe there's a mistake.
Let us understand the structure of this expression.
Yeah, okay.
Yeah.
So maybe we can look at its transpose, its transposition, and I think it's anti-symmetrical, I guess.
Exactly, yeah.
Anti-symmetrical. So on the diagonal there's just zeros here.
Why?
Because this is
Antisymmetric. Yeah, yeah.
But if this produces no elements on the
So,
diagonal,
I'm sorry. Why it's anti-symmetrical?
or is it? I just when we transpose it. Oh, yeah, yeah. Antisymmetrical in the sense that if we transpose it, we get the same thing with the opposite sign. If we transpose this matrix.
Could you write it? Could you write
Yeah,
it?
just to understand
Because-
the structure, let us transpose it. And so, I guess, So it's the same. So it's symmetrical. Right?
Why? No.
No. So fully transposed. So it is. Right?
Yeah, yeah.
And the same for.
Yes, it's
the other
symmetric.
term, so
It's symmetric.
symmetrical.
Very good.
Um,
It's better because we have somewhere the derivative of a.
Yeah, but with regards to if there are off-diagonal elements, I don't think this. So I think we just need to multiply and see, right?
Okay.
Or maybe there's.
No.
tricks.
No. It's better to multiply.
Okay. So we have. If we multiply by the by the transposition, there's some space. So we get on the diagonal we get v1 squared. Then there is nothing. So this is B times B transposed.
Mhm.
So
But could you imagine the general rule of composition of two matrices of such form, of upper over diagonal and of lower one diagonal, but Jacobian matrix? I like to say that in general situation, their product is diagonal matrix.
if they are independent of each other.
Yeah.
Ah,
Because you see, this matrix acts like a lowering operator, just a shift on the basis vectors multiplying by some constants, but lowering the index. And this acts by acting on index by addition by one.
Okay, I see.
The composition always preserves the grading, maybe multiplying by some coefficients, but the product is always a diagonal matrix in all orders. The commutator else.
Okay, and so.
So it is always a diagonal matrix.
And so for B transpose B, this is. So for B transpose B, so it just shifts.
Yes, and we, yeah.
And so let me write down the result. So the commutator is
B1 square. b2 square minus b1 square. Mm-hmm.
Okay. So we in fact can identify the derivative of d with this commutator.
Very good. Yep.
And so this is just a j its derivative then 2 by so 2 by b j squared minus j
Minus 1.
minus 1
square.
where we set b 0 to 0.
Mhm. Yeah.
So this is satisfied, and then we move on to this one.
Mm-hmm.
So this is 0.
Do you know the commutator of the matrix element with the diagonal matrix?
So this I think it's just
No.
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 Okay. Oh no, okay. Yeah. So this is just a diagonal where there's just one element.
No, with all elements.
With all the elements. And they're different.
Yes, generic element.
Yeah, I don't remember this formula.
Mhm.
But okay.
It's quite useful.
So
Maybe it's better to write it in the sum a k e k k.
okay.
Sum over k, and this e k k interact with only if k is equal j and if k is equal I, only in these cases. So there are only two summand in this sum which would be non-trivial.
And so
But the result is always eij.
so yeah.
So it's proportional to eij. Mm-hmm. Very good.
And so it is I think here we have the Kronecker symbol.
You have already Kronecker symbols when you have chosen.
So this is a matrix where the only one element is set
Yeah.
to 1. Okay.
Yeah. So it is already the application
Ah.
of the Kronecker symbol.
Okay. So in this notation,
Yeah.
it's just this. With
ij
ij.
and minus. because it's a coincidence of these indices.
Okay. Mm-hmm.
Okay,
Mm-hmm.
and plus.
Yeah.
Uh-huh. No.
No.
Also
Mhm,
ij,
mhm, mhm.
because now it's a coincidence of such indices,
Mhm,
and it is the term with plus,
mhm,
and we get ij here.
mhm.
This is ij. Yes, that's right, and it is ij, aj minus ai.
Okay. So here. So using this formula.
Yes, of course. Yeah. You see, all this coefficient, all these terms
Yeah.
will stay at the same matrix place, because it is here the same element, but it will be multiplied by some coefficient, by the difference of eigenvalues of the matrix D, corresponding to the numbers.
Okay.
So this B1 will be multiplied by A2 minus A1.
Yeah, okay.
Okay.
And it is.
Yes.
Okay.
So yes, I think you understood.
Just many facts that I don't know.
Uh-huh.
Yeah, I'm saying like many arithmetic calculations.
Yes, but not infinite number of tricks.
So that's finished.
Yeah.
Okay.
Thank you very much. We finished for today. Good continuation today, and see you next week.